So I would like to talk today about some fundamental physical limits to information processing, and I put in living systems here in parentheses because what I'm going to be talking about also applies to non-living systems, but my main interest is, of course, in living systems. So the motivation for this is twofold. First part of the motivation would be to ask, I want to know about information processing and learning and adaptation in living systems. So one thing that's kind of a dream is, are there any kind of simple physical principles underlying the apparent magnitude of the effects and events in biology? So if you first glance at biology, there's really a lot to be understood and summarized, and maybe are there some simple principles that combine all of these different effects? And this is closely connected to the question of what are the physical limits. And so here I'll focus on the physical limits of information processing, because we know that biological systems process information, they learn, they adapt, and they're also embedded into stochastic environments and often adapted to those. So one organism that may be adapted in a better way than another organism may have an advantage evolutionary, so there may be more of those organisms. So therefore looking at efficiency arguments may actually lead us to the discovery of what are sort of building principles underlying those organisms. And two candidate principles here are, of course, the efficient use of energy and then also the efficient use of information, so efficient information processing and modeling, if you wish. And those principles, or talking about these principles, has a very long history, and I don't want to go into it, but I also want to point out that it's still quite modern. So just a couple of years ago, Terry Sanowski's lab came out with saying that metabolic cost may be the unifying principle governing neuronal biophysics. And Bill Vieques just published a book last year where he looks exactly for principles in biology, and he mentions that information processing is crucial for organisms, in particular separating predictive information from the background of non-predictive clutter is really important. Now, the other way in which I could motivate what I'm doing is simply by saying that nature, not only living systems, but nature processes and transforms information, and most interesting systems run at finite rates, and they also operate far away from equilibrium. So if I want to ask about some fundamental limits here, if I'm interested in thermodynamic limits in those processes, then I gotta try to describe this, and so I have to step away from equilibrium thermodynamics, which is of course the first thing I want to look at if I want to know about a connection between information and energy. So looking at work going back to, you know, the classics, Boltzmann, but also Shannon, Jaynes, etc. There are too many names to put here in all of these columns, you know, like, so that's what the little dots are for. If I look at this equilibrium, this regular equilibrium stat mag and information theory, then Landauer in '61 made this argument that if you erase some information, which is basically you're decreasing entropy in the system, then you have to pay for that by the generation of heat. So that sets a natural limit to computation. Like I said, I want to look at systems that are not necessarily in thermodynamic equilibrium, but that can be driven arbitrarily far away from thermodynamic equilibrium. Now, fortunately, since about 15, 16 years, there's been new development in this area, mostly due to the work of Jasinski and Crookes, but many, many, many other people. Stochastic thermodynamics then allows us to realize that when a system is out of equilibrium, there is an additional available free energy. And we can possibly harvest that. So that has motivated a whole area, which is also quite fashionable right now, where you can use a measurement of the system to control the system to lower the dissipation. However, like I said, my systems that I want to study are not only far from equilibrium, but they're also embedded in stochastic environments, and this is not part of the setup. So I need to go one step further, and then when I look at efficiency arguments and thermodynamic efficiency in these systems, I find that the instantaneous dissipation due to some change in an environment is basically proportional to instantaneous non-predictive information. And so I'm going to try and elaborate a bit on this point in this talk. This also gives me as a corollary of a refinement of Landauer's argument. And the nice thing is that the main result carries over to quantum systems and allows for a new interpretation of quantum discord. So I have lots of slides, lots of material, lots of equations, no pictures, no movies. I'm sorry. So brace yourself. If you don't understand every detail, it doesn't matter. Just remember this. So I want to just give a quick sort of reminder of equilibrium thermodynamics, because, you know, why not? It's fun. So let's say you have some gas in a piston, and this is assumed to be in equilibrium, so it's sitting in a heat bath. Then you can describe this by the Boltzmann distribution, which according to Jaynes is of course a maximum entropy distribution given the measurements you have. So here in this case it would be the average energy. And the entropy, again I'm quoting Jaynes here, the entropy, the thermodynamic entropy is related to the Shannon entropy of the equilibrium distribution just by a scaling factor. So this is by no means non-controversial. I would say that some people maybe in this audience would argue that, which would be good, but this is the line of thought I'm going to follow. You can then define a free energy, which is basically the available energy that you have in this gas. Now, you can do work on this system, so you can push the piston in, and doing this work changes, of course, the available free energy. And so the second law of thermodynamics tells you that you can never get more work out of the system than you put in on average. So the dissipation here is the entropy production. So on the one hand, it's heat produced. So the convention here is that positive heat would be heat flowing into the system. So negative heat is heat produced. And it's also the change in the system entropy. And that has to be non-negative. If you push this in arbitrarily slowly, so quasi-statically, then you can get to a situation in which you don't waste any work, but it's also not very useful because it's very slow. Once you push it in quickly, you drive the system out of equilibrium. Now, just using this equilibrium argument, Landau pointed out that the second law of thermodynamics basically tells us that in order to erase one bit of information which comes along with an entropy change, we have to produce heat. And so this is the absolute limit on what we can do. Now, like I mentioned, living systems are not in equilibrium. For example, things that help you think, things that transport stuff around in your cells, things that move your muscles, and things that charge your batteries, so to speak, are not in thermodynamic equilibrium. As a matter of fact, you mentioned Schrödinger's book. He phrased it this way: the decay to thermodynamic equilibrium could be understood as death. So thermodynamic equilibrium for living systems, maybe not the most interesting description. Now what happens away from thermodynamic equilibrium? Thanks to Christopher Jasinski, we have a new relation here. So if you remember in the previous slide, the second law of thermodynamics, right, it tells you that on average you can't extract more work than you put in. So the work you put in always has to be greater or equal than the equilibrium free energy change. This is known as Claudius Inequality, and it's an inequality. Now, thanks to Jasinski, we have an equality which holds arbitrarily far away from equilibrium. So the equilibrium free energy here can be expressed as something that depends on the path, and this is the ensemble average. This is very nice, and you see immediately that using Jensen's inequality, you can get the previous statement out of this equality. But furthermore, if you assume that there's Gaussian noise and you expand this right-hand side into the sum of cumulants, that you can also get a fluctuation-dissipation relation out of this equality. So it's very nifty from a theoretical point of view, and I just wanted to show it to you because I like it. I'm not actually going to use it. You can also use this to measure equilibrium quantities in experiments that are never really in thermodynamic equilibrium. And I don't want to go into the details because there's no time, but this is a fascinating area. Now, Gavin Crooks, my collaborator, produced in his thesis a derivation of the Resurgence relation that's extremely elegant. And because I like it so much, I'm going to show you that one too. So don't get scared by the next slide. You don't need to understand every single detail. There. So, the way he thought about this is, he said, let's assume that a system can take a stochastic path through its state space, so the states of the system are given by these S variables here. And let's break time apart into little steps, and so there's these little work steps where the environmental variable changes and we do some work on the system, and then there's a little relaxation step where the system follows. And in the work steps, we do work. In the relaxation steps, the system exchanges heat with the heat bath. So we can write down the work and the heat broken up into these incremental steps. Now, we can ask for the total probability of a path through the state space given an external protocol. So given that we run a protocol x0 to x tau, where these variables are now known, we can ask what's the likelihood of the system going through a path in its state space, and that would be this probability here. And then equally, we can ask what's the likelihood of finding the exact inverse path if we put in the exact inverse protocol. So if we start the system in equilibrium with this external parameter being the last parameter of the forward protocol and we run the whole thing backwards in time, then what's the probability of the system going through the exact time reversed sequence? And you write down the ratio of these probabilities to compare them, and you find that this is exponential in the work you do in excess of the equilibrium free energy. And with this, you can show the Resurgence relation in one single step. So it's very nice. So, however, this still assumes that you start and end in equilibrium. So on the forward path, you start in equilibrium here. On the reverse path, you start in equilibrium here. And you're still comparing equilibrium quantities. So this is the equilibrium free energy, right? But I can't really use that, because what if I want to talk about systems that are never in equilibrium? Then I need a notion of dissipation away from equilibrium. So here's a silly little sketch that more or less comes out of this paper. I've changed it a little bit. So assume that you start a system in equilibrium and then you drive it away from equilibrium. So this would be just a trajectory that indicates the distribution of the system, going away from the corresponding equilibrium distribution at some time. So because you're not in equilibrium, you have additional free energy, and this additional free energy is proportional to the relative entropy between the actual distribution and the corresponding equilibrium distribution. This quantity happens to be a Lyapunov function. We know that from Schlöger's work. So we then say that dissipation must be the work irretrievably lost. So it's not, dissipation is not the work you lose after you push the system away from equilibrium and then wait until it relaxes back to equilibrium, and then you harness the work, right? Which is the classical picture. You can do better. Maybe you can't because you don't know anything about the system state, but in theory you could do better. But but work that's really irretrievably lost is the work you've put in minus the non-equilibrium free energy change. So at each point in time you can assign a non-equilibrium free energy, which is basically the equilibrium free energy you would have if at the same value of the parameter. So this would be like the location of the piston in the case of the gas. If you let the system relax back to equilibrium, right? This would be the equilibrium free energy. And in addition, we add this additional free energy to it. That gives us a non-equilibrium free energy. And then dissipation is understood as the work done in excess of that non-equilibrium free energy change. Now this is related to the work done in excess of the equilibrium free energy change, trivially by this relation, and this has spurred a whole research field, and I have to hurry up. But we have to do a little bit better because our systems are embedded into stochastically fluctuating environments. So the setup here is more like in a machine learning setup. The environment produces some variables which drive the system, and the system evolves in time. And I'm going to take the interpretation that the system dynamics implement a model of the environment. And then I can ask the question, what is a good model and what is a bad model? And I can judge model making or information processing that way. So we have a simple framework here in which a signal contains predictive information, and a system may extract this predictive information. So this comes back to Christoph's question here, right? We discard most of the information. We can go into this in the discussion. So some of the information that the system extracts, so some of the memory that it has, may be indicative about what's going to happen in the environment in the future. And a measure for ineffectiveness or inefficiency of this information processing is then the remainder, the non-predictive information. Okay, now that I've specified how I want to measure the information processing inefficiency, namely by non-predictive information, and how I want to measure thermodynamic inefficiency, namely by dissipation, which is based on non-equilibrium free energy change, now it's easy to see that these two things are very closely related to each other. So the amount of energy that's dissipated in this instantaneous change here when the environmental variable changes is proportional to the non-predictive information contained in the state of the system. So that is maybe the core insight, and the nice thing is that this carries over to quantum systems and allows you to interpret discord as the thermodynamic efficiency of the most energetically efficient classical approximation of a quantum memory. And so you can also ask, is there like a quantum advantage here? And there can be, but only if the environmental variable is quantum, not if it's classical. So another corollary of the main result is a refinement of Landauer's argument, where we see that his bound now becomes augmented by the non-predictive information. So I want to show you my punchline, which is that dissipation of energy is fundamentally related to non-predictive information, which is a measure of information processing inefficiency in some sense. And so I want to make some provocative statements here, which is that maybe in order to operate at some maximal thermodynamic inefficiency, living systems have to predict. And so therefore, maybe predictive inference, which is something that we really kind of pride ourselves on as conscious beings, may not be restricted to a higher cognitive function. But maybe some of these biomolecular machines that you talked about, that some of them are very efficient, might have to implement this too on some level. And finally, we could ask whether prediction or predictive inference may be a signature of life. So then if I still have some time, it would be nice to look a bit closer at predictive inference. What is it? Like I mentioned before, we say here that some part of the memory contains information about the future, and so we can turn this into an optimization problem. We can derive optimal predictive machines, lots of theorems and algorithms about them. In particular, we know that the best predictive machine is something that's known as the epsilon machine, which is basically a constant state partition endowed with the dynamics. And now we can go a step further and ask about, what about feedback? What if my system can interact with the environment in such a way that the actions of the system change the environment and therefore the future that the system itself will encounter? Then we can extend all of these notions of causal state partition and epsilon machines to this framework, and maybe more interestingly, we have a result that says that an optimal action policy that's optimal in the sense of prediction must balance between exploration and control. And finally, we can ask, and then I want to mention that the thermodynamics of this feedback situation are not yet worked out, and we're working on this together with Gavin Crooks and also with David Sivak. And then finally, we can ask, what about quantum systems? What would be optimal quantum predictive systems? What are the corresponding theorems and algorithms here? And are there any intrinsically quantum advantages we can get to prediction? And this is work I'm currently doing with Arne Grimsmo. So I would like to thank all of my collaborators over the years, and here are some of my students that have worked out some specific cases. Bill Bialek is the guy from whom I have learned the most, and then David Silva, Gavin Crooks, and Tony Bell are the ones with whom I did this work on the connection between prediction and information. Thanks.